Welcome to Lecture 21, Evolution of High Mass Stars, Part 2. In the last lecture, we started talking about what the differences were between the evolution of high mass stars as compared to their low mass cousins. And we discovered that there were a couple of main things that were different. The first is that different types of nuclear reactions can occur. In particular, the CNO process fuels the main sequence lifetimes of high mass stars. Just because thanks to the high mass, the temperatures are hotter in the core, and these CNO reactions are more efficient. The other thing that we discovered is because of, again, the higher temperatures reached in the core of high mass stars, additional levels of nuclear fusion reactions can occur that were inaccessible in low mass stars. So today we're going to build on that, and we're going to start off with a quick review. And then we're going to go into some detail about a term that I introduced last time, namely the R process, in which so-called high Z elements, by which we just mean high atomic number elements, or the elements lower down in the periodic table, are produced near the end of stellar lifetimes, which cannot be produced during the lifetimes of the stars themselves. So let's jump in and see where we get. So as a quick summary of what we discussed last time, one of the main takeaways of high mass stars and one of the distinguishing properties of these stars as compared to low mass stars is this onion-like structure that develops by virtue of the fact that so much more nuclear fusion can occur. So remember, in low mass stars, you can fuse hydrogen to form helium. You can fuse helium to form carbon, but that's it. Temperatures in low mass stars never get high enough to fuse carbon to form anything heavier. But that's not true in high mass stars. High mass stars are more massive, and they're hotter. And because they're hotter, they are hot enough for carbon to fuse to form silicon and sulfur, for example, silicon and sulfur to form oxygen, neon, and iron, and so on. And so we develop this onion-like structure. I've said this before, and I'll say it again, this is decidedly not to scale what you're looking at right now. The vast majority of the volume of the star is always a non-burning hydrogen plasma envelope. But again, if we drew this to scale, you wouldn't be able to see anything, and so you pick your poison. The other thing that I'll remind you of is how quickly the time scales speed up with each stage of stellar evolution. Remember, high mass stars burn up much more quickly than do low mass stars because they're so much hotter, and the nuclear reactions that fuel them proceed so much more quickly. So it might spend a handful of millions of years on the main sequence. I chose 7 in this particular slide, but you step through with each subsequent level, it's something like a factor of 10 reduction or more in terms of how long the process takes. By the time you get to the silicon fusion to form iron, you're talking about a day for the entire star's supply of silicon to be fused to form iron. And so eventually you build up all of this iron in the core, but as we discussed last time, when I gave that glorious plot of average binding energy per nucleon as a function of nucleon number, iron is the most stable nucleus in the universe. Okay, and so as long as you're fusing lighter elements to form iron, you're releasing energy. But once you get to iron, if you were to fuse iron with anything, it would require energy being put in. And so nature is not going to do that of its own volition. And so fusion stops with iron. Well, as more and more reactions produce iron, the mass of the iron core gets larger and larger. Eventually, gravity wins over the degeneracy pressure that's supporting it internally, and the iron core collapses. And that collapse takes place in less than a second, and it is cataclysmic for this star. And so just to remind you what happens, this is what initiates a so-called core collapse or type 2 supernova. I'm not going to go through every step because we did that in the last lecture. If you want to do it again, you're welcome to pause me and take a look at this slide, or you're welcome to pause me and go back to lecture 20 where we did discuss it in some detail. But the upshot is that eventually the iron core collapses. It rebounds off itself in just a mind-bogglingly violent shock wave that then propagates through the outer layers of the star and just blows the vast majority of the star to smithereens and ejects that mass and all of those elements that it's created out into the interstellar medium. But it doesn't completely destroy everything about the star. It does leave behind a remnant, and this is, sort of the first exotic astrophysical object that we've run into. It's often referred to as a compact object for reasons that will become clear shortly, but it's this neutron star that sits here, very small dot here in this picture. So this is kind of the high-level final stage, again, that occurs in less than a second and really just cataclysmically destroys the star. Okay, so we spent some time in the last lecture talking about the creation of elements, because one thing that we've sort of come back to periodically throughout this series of lectures is the fact that the interstellar medium is comprised of hydrogen and helium, right? 90% hydrogen, 10% helium or so by atom number. And so that's what makes stars. And stars then are kind of like, they're nuclear furnaces, and they create heavier elements through the process of nuclear fusion. But what we've said now is that fusion stops with iron, because iron is the most stable nucleus in the universe, iron 56 in particular. And so we've made most of the elements leading up to iron, but it is important to note we made most, not all. There are still 3 outliers here if you look closely: lithium and beryllium down here, and then boron has also not been made through any of the fusion reactions that we've discussed. So kind of file that in your mind somewhere. But so far we've made most of the elements that we observe in nature up to iron, but we haven't made anything past that. And so the question that we, very near the end of the last lecture that we posed is, well, if we can't use fusion, as we've discussed it anyway, to make any elements heavier than iron, where did all of those elements come from? Because we can go, not necessarily out into your backyard, but you can go out somewhere and we dig up, lots of these elements in nature. Obviously, we've got lots of them sitting around. So where did these come from? And the answer that we got to at the end, that I'm going to spend some more time sort of trying to convince you of today, is that these are produced in supernova themselves. So it's really, I want to sort of impress upon you the fact that we've talked about at least millions of years for these high mass stars and billions of years of lifetime for low mass stars, through which they slowly churn out these heavier elements. You think about it, the sun, sort of the generic G-class star that it is, it's going to take about 10 billion years just to convert all of the hydrogen in its core to helium. Okay, so we're talking about billions of years to produce, just the second lightest element in the universe. Now, obviously, higher mass stars do it more quickly, but again, only 3% of stars in the universe are high mass stars. So it takes a long time for that first stage to occur. Each stage after that occurs more quickly. But now we're in a situation where we're talking about less than a second for the core collapse supernova to occur. And my claim to you is that in that 1 second or less, you produce basically every element above iron. So given that I've told you that iron is the most stable nucleus and we don't fuse past that, how does this happen? What's different about the supernova process that allows us to make these heavier elements? So this process that we're going to talk about now, that's responsible for generating all of the higher Z elements above iron, is known as the R process. And R just stands for rapid because, as I've said, this is an extremely rapid process on the time scales of stellar evolution. And the first thing that the first point that I want to make is that this is a highly non-equilibrium process. And we could go into a lot of detail and won't about what is meant by non-equilibrium. But what I mean in this context is that during most of the star's life, these fusion processes occur because they release energy. You're combining nuclei to form a lower energy state, and then you release energy. It's the nuclear equivalent of a ball rolling downhill. It will do so naturally, and kinetic energy will be, you will convert potential energy into kinetic energy. A ball will not spontaneously roll uphill, and similarly, iron, once it's formed, will not spontaneously fuse to form something that is a higher energy state. But during the stage of stellar explosion of this supernova, so much is happening so rapidly that essentially the constituents, the particles and the nuclei that are in the star, don't have time to find their true lowest energy state. And in particular, during the supernova, just a gargantuan number of extra neutrons are streaming through the star's envelope. So the core is extraordinarily small compared to the star's envelope, right? And so as it explodes, just gobs and gobs of neutrons are just slammed into all of the nuclei that make up the star. And there's so many that these neutrons effectively pile up on the surface of the nuclei. And this leads to a process known as rapid neutron capture. You can kind of think of it as if the nuclei, if left to their own devices, really would prefer not to have those neutrons. They're more stable without them. But those neutrons are being shoved onto the nucleus, so the nuclei don't have a choice. And so given that, the nuclei then say, well, the next best option is to figure out how can I stabilize myself in some way. And one way that it does that is by converting neutrons into protons. Because in general, nuclei prefer to have roughly equal numbers of protons and neutrons. The most stable nuclei tend to have roughly equal numbers. Though it's worth noting, as the nuclei get larger, they do develop an asymmetry such that they do have more and more neutrons relative to protons. But still, there are so many neutrons being captured that some of these neutrons get transmuted into protons. And when they do that, they move up the periodic table. Right? Because the proton is what the number of protons is what determines where the element sits on the periodic table. So the R process is just a very rapid process in which floods of neutrons are forced into the nuclei of the star, and then through conversion of some of those protons some of those neutrons into protons, those elements kind of walk their way up the periodic table, gradually making higher and higher Z elements. And when I say gradually, I don't mean in terms of long time scales. This happens very quickly, but it's a sequence. So you can imagine an iron nucleus having 30 neutrons piled up on it, and then kind of in very quick succession, a number of those protons or neutrons would convert into protons, and you might move 15 spaces up the periodic table or something like that. So that's the R process. There's a lot of complicated physics in it, as you might imagine. And as I've said many times, people have and continue to spend their careers on those details. So if you're interested, there's plenty more out there to read about. So the R process now is what's responsible for making a huge number of the heavier elements here, and you can see that in red. Now that we've introduced the notion of an S process or an R process, it's natural to also define the term S process, which, as you might imagine, stands for slow process. So everything that we talked about before the R process, we're now going to call S process. And so what you can see from the color coding on this periodic table is that some elements are produced only through S process, which is the normal nuclear reactions that we talked about before we got to high mass stars, and some of the slower reactions in high mass stars. Some nuclei are only produced in supernova in our process. But then there are some that are produced both in supernova and in large stars, and some that are produced both in small stars and large stars. So there are some multicolored elements here, but there are a lot that only appear in one way. Now, it turns out, and we are not going to go into detail on this, but it turns out that you can do a very quantitative analysis using the known physical laws of nature as we know them today. And you can calculate, given everything that I've told you, exactly what we would expect the natural abundance of the elements to be. In other words, if the universe started off with 90% hydrogen and 10% helium, and stars formed and they produced heavier elements through all of the processes we've discussed, what would the result be today? And when you do those calculations, you get a plot that looks like this. So on the vertical axis, you have the number of atoms relative to hydrogen. So hydrogen is 1 by definition. And then the question is, how much helium do you have? Well, it's about 10%, a little, about 10% of hydrogen. So it's down here at 10 to the minus 1. How much iron do you have? Well, it's down here. You have a lot less iron than you do hydrogen, but you still have more iron than you have of several other things, because again, iron is very stable. So you get this sawtooth pattern that's characteristic. It's a result of some fairly detailed nuclear physics we won't go into, but the theory produces this kind of sawtooth pattern. A couple of other things that I'll point out, and I've made this comment a couple of times before. 3 particular elements are destroyed, rather than formed in stars. If they occur in the star, they're destroyed through nuclear reactions, and they are not formed at all in stars. And those are lithium, beryllium, and boron. And so one thing that's interesting is, if you do the calculations again, you'll find out you're basically not going to produce these elements. And so the question is, well, if you look in nature, how much of these things do you actually find? And the answer is, you don't find very much. They're there, so we still have to understand and explain why do we see these things at all. But it's noticeable that the lithium, beryllium, and boron are in much lower abundance than anything else that's next to them in the periodic table. You have a lot of hydrogen, a lot of helium, a relatively large amount of carbon, nitrogen, and oxygen, but then very little lithium, beryllium, and boron. So the good news is that the calculations do a good job of not exactly matching nature so far as I've told you. It is encouraging that the calculations would say we should have none of this, basically. And when we look, we have not none, but very, very little. And then again, the iron kind of has a peak here because it's the most stable element in the universe. It is the end result of any S process, any slow process, nuclear reactions in stars. Only produced in high mass stars, right? Not in their low mass cousins. But you see a peak here because once you form iron, it's going to stay iron until and unless it suffers in our process events. Then for these more massive elements, these are all formed by neutron capture in the R process. So, this slide is a nice sort of point to pause and recall something that was in the, back in module 1, back in the very first couple of lectures, made the claim that, you're made of stardust. You're made of, the stuff of stars. And, all we mean by that is that, you've got a lot of different elements in you, we all do. And you can look at the percentages here, but the current theory is that all of these heavier elements are produced in stars. And again, to the theory's credit, the numbers that you calculate, the relative abundances of the elements match very well to what we observe in nature. And this really, I can't emphasize enough that fact, the fact that our using the laws of nature as we know them to calculate what we would predict the natural abundance of the elements to be, and then finding that that matches so well with what we actually observe in nature is one of the greatest achievements of modern, certainly of modern astrophysics, and I would argue modern science. And then we again have the this core collapse supernova that we introduced at the end of the last lecture, kind of, which is the ultimate end of a high mass star, in which you have this just cataclysmic explosion. You throw lots of stuff, certainly lots of light elements, but relatively lots of heavy elements as well, out into the universe. The shock waves that are sent out in this way can help see, as they pass through giant molecular clouds in the interstellar medium, they can help seed stellar formation, the formation of new stars. And the energy involved in this is really, it's hard to wrap your mind around. The energy involved is on the order of 10 to the 46 joules. So that's 1 with 46 zeros behind it. And those neutrinos that I've mentioned a handful of times, but that we mostly ignore, 99% of the energy that's released is in the form of neutrinos, which is that's kind of mind-boggling. Almost all of the result of what's left, the 1%, is in kinetic energy, which just means the energy of motion of the nuclei that are being ejected into space. And then a measly 0.01% or so comes out in the form of visible light. But as I've mentioned before, that's enough to make these things extremely bright. And so it's 1 part in 10,000 of the energy comes out in the form of visible light, but it's still extremely bright. And so we can see these things from very, very far away when they occur. So at the very end of the last lecture, one thing that I introduced, a term that I introduced that you may have heard, it comes up in the news periodically, and it's sci-fi likes to reference them to, is the neutron star, right? So as means of comparison, when we were discussing low mass stars, we commented that a low mass star ends its life in the form of a white dwarf, right? Sends off a planetary nebula, about half of the mass of the original star is lost in that way. So about half of the mass of the original star is left in the form of a white dwarf, which is a hot, dense, degenerate carbon and oxygen ball, but it's not hot enough to fuse, and so it just gives off thermal radiation until eventually it cools down and vanishes. So a white dwarf has roughly half the mass of the sun, say up to the Chandrasekhar limit of 1.4 solar masses, so no more massive than 1.4 solar masses, and it's roughly the size of the Earth. So obviously a lot more dense than anything that we interact with on a daily basis. Well, a neutron star takes it to a whole nother level. A neutron star here is much, much smaller than either the Earth or a white dwarf. And so the densities, as you might imagine, are correspondingly mind-bogglingly large. It really is hard to wrap your mind around how dense it is, because a neutron star, in terms of the density, has the density of a nucleus, basically, right around there. It can be more, but it's on the order of the density of a nucleus. So you've heard, I've told you, and you probably heard in some high school science class, that most of the space of an atom is empty. And there are some, I would like to put some caveats on there, but I don't want to get derailed. The point is that a nucleus is just extraordinarily dense, but then the electron clouds that surround that and define the outer, sort of the size of the atom, are much larger than the nucleus. And so the overall density of the atom is kind of normal, for us. But a neutron star consists of nuclei, that have overlapped essentially to the point that it's just a huge collection of neutrons and other subatomic particles. And so the density is really almost impossible to fathom. But if you try to fathom it and you look at the structure, There are a few things that we can say about this. Firstly, the mass of neutron stars will vary, but a good estimate for an average is something around the mass of the Sun, 1.5 times the Sun. One very interesting question that is still outstanding today and is the subject of quite a bit of modern research, both in theoretical and observational physics and astronomy, is what is the possible maximum neutron star mass? Because just like there's a maximum white dwarf mass, the Chandrasekhar limit, there is also a maximum neutron star mass. And people have calculated what they supposed that maximum mass is for 70 years. As a matter of fact, Robert Oppenheimer was involved in that kind of calculation before he took over leadership of the Manhattan Project. So that's an interesting bit of history that if you're interested, you can look into or ask me more about. But over and over and over again, what has happened is someone has used a theory to calculate what they believe the maximum neutron star mass to be, and then we have observed a neutron star more massive than that. So then the theorists go back to the drawing board and calculate again. They modify their theory and they say, okay, made a mistake the first time. With this new term in the equations, I get a higher neutron star mass, and so I can explain that observation. But then someone else comes along and measures a yet higher mass of a neutron star, and so the theorists go back to the drawing board again. And so this has been happening over and over again, essentially since the late 1930s. Today, there have been a few observations of neutron stars with masses of 2 solar masses, essentially with some uncertainties that are relatively small. So we're confident. We know that you can have neutron stars of at least 2 solar masses. We're making a lot of observations of neutron stars now. Recently, technology has gotten much better at being able to do that. So there's a lot of data to suggest that neutron stars do not form much more than 2 solar masses, but the precise cutoff is still outstanding. They tend to have a radius of around 10 kilometers, diameter of 20 kilometers or 12 miles or so. They do vary depending upon the mass. But that's a good estimate. So think you've got something that has a mass around the mass of a sun that's crammed into a sphere with a radius of 10 kilometers or so. So again, mind-bogglingly dense stuff. It has what's called a crust, which is solid. What the properties of that solid crust are a topic that people spend a lot of time studying. And then the interior we believe to be, well, actually there are lots of theories. Here it's labeled a heavy liquid interior, consists of a lot of mostly neutrons with other particles. That's one idea, but that's far from it. It's far from certain. What is certain is that we can't go visit a neutron star and scoop out a spoonful of it to go investigate it. As it turns out, I did a good part of my my PhD work studying neutron star properties and the properties of the very dense nuclear matter that make that up. And so I could go on and on about this and would love to, so I'll cut myself off. But really, if you have any questions about this or would like to dig further into neutron star properties, please don't hesitate to reach out. One other thing that I'll leave you with is that because, as you can imagine, if you take a huge amount of mass and compress it into this, very small volume for, as far as astronomical objects are concerned, the gravitational field that it creates near its surface is absolutely enormous. And so one way of quantifying that is through the escape velocity, which is just the speed required to escape the gravitational field. And the escape velocity of a neutron star is more than half the speed of light. And so, like if you were standing on a neutron star, first of all, you couldn't, you would almost instantly be pulverized by gravity. But if somehow there were a beam of light leaving the surface of a neutron star, light would make it out. But if you were going less than half the speed of light, you would not make it off the surface. So really exotic astrophysical object that understandably is the subject of a lot of interest and current scientific research. So now neutron stars, in addition to being very massive, or to being sort of massive on the order of the sun and just extraordinarily dense, they also tend to spin. And this shouldn't be a surprise because we've seen this over and over again. Lots of things in the universe spin. You know, just as when it comes to stars, they have been spinning since they first started to form, right? Every time they collapse, they speed up. Just like if you watch a figure skater, if a figure skater has her arms out, she spins relatively slowly as she pulls her arms in, reducing her moment of inertia. If you want to put a technical spin on it, pun intended, then that rotation rate will speed up. Well, the same thing happens to a neutron star. And because a neutron star is extremely small, it rotates extremely quickly. And so, you know, if these things weren't exotic enough and hard enough to wrap your mind around, it just got worse. Because a normal star is big and has a relatively small rotation rate and a relatively weak magnetic field. A neutron star is extremely small. It spins correspondingly very quickly and has a capital strong, very strong magnetic field. And so these really are things that you can't make anything like this in a laboratory. It takes, you know, it takes stars to make these things, and not just run-of-the-mill stars, but massive stars. So because neutron stars spin so quickly and they have such strong magnetic fields, some of them are observed in the form of something known as pulsars. And the reason, if it seems weird that we would say, we've named this thing a neutron star, but now we're going to call it a pulsar too. The reason is that pulsars were observed before we knew what they were. And so eventually we realized that it was just neutron stars that were giving rise to these pulsars. And so a pulsar is a neutron star, but it happens to be one that emits light in jets along the north and south magnetic poles, and as it spins, that jet sweeps out. It rotates about the axis, sweeping out a cone. And as you can imagine, most neutron stars, they aren't everywhere. I mean, there are a lot of neutron stars out in the universe, but there aren't a lot very nearby us. And so since it's only shooting out jets along the axis, most of the time a neutron star's jet is not going to be pointed towards Earth. So most of the time we just won't ever see those jets. But some neutron stars will happen to be rotating in such a way that the jets are pointed towards Earth. And when that happens, when that light cone, when it sweeps out that conical shape and the light happens to be pointed at Earth, we can observe that signal. And so we will observe a periodic signal or a pulse such that every time it rotates, we'll see a flash. And so in the early days, that's what was observed. We observed these periodic flashes of very intense light, and the question was, we could tell these things were very far away. And so the question is, what on earth could be energetic enough to send this kind of intensity at Earth from millions or billions of light years away? And the answer, as it turns out, was a very rapidly rotating neutron star. So as an analogy, a pulsar is kind of like a lighthouse. The light is always on because this neutron star is always spinning, but we can only see it when it happens to be pointed at us. So pulsars are a lighthouse, the astronomical lighthouses. And if just like you don't want to run into the rocks on a ship, you do not want to run into a neutron star. So let's back up now and summarize sort of the highest level evolution of stars. So stars begin their lives in a stellar cloud with protostars, right? So giant molecular cloud in the interstellar medium, gravity begins to condense the cloud into these little clumps, and those clumps are known as protostars, which eventually, if they become hot enough in their cores, evolve into true stars. So 97% of those are low-mass stars, and a low-mass star sits on the main sequence for a while, eventually turns into a red giant, and then eventually gives off half of its mass or so in the form of a planetary nebula and leaves a remnant of a white dwarf. On the other hand, 3% of the stars in the universe are massive stars. Those massive stars evolve much more quickly on the main sequence. They evolve into red supergiants. Those supergiants are hot enough in their stellar cores that they can fuse higher Z elements, eventually stopping at iron because that's the most stable nucleus. And then eventually that iron core will become too massive, it will collapse and destroy the star in the form of a supernova. And that supernova will take most of the mass of the star and throw it out into the universe, but it will leave behind a small remnant, which is very often a neutron star that we just talked about, but not always. There is another possibility because, as I alluded to recently, it turns out there is an analog of the Chandrasekhar limit for neutron stars. So just like there's a limit to how massive a white dwarf can be, there's also a limit to how massive a neutron star can be. What happens if you're too massive to be a neutron star? And here we get to the second exotic element or astrophysical object of the day, and one that is even more popular than neutron stars, and that is what's known as a black hole. We will say more about that in the time to come, but I told you at the beginning of the semester, astronomy has lots of exciting things that go on. I've now, for 20.5 lectures, forced you to listen to me talk about the evolution of stars and gravity and Kepler's laws and lots of other things, but now we're finally getting to the exciting stuff that even pop culture likes to talk about in the form of neutron stars and black holes. So more to come. So one thing that I want to remind you of now is the notion of a star cluster, which is just the fact, if you think back a handful of lectures ago, when stars form from the interstellar medium, they tend to do so at the same time as other stars, because if you have a collection of gas, that globular cluster doesn't just form, or that nebula won't just form one star, it'll form lots of stars out of the same huge cloud of gas at very similar times. And so there are there are different classes of these star clusters. There are some known as open star clusters in which stars are actively forming. And so here you can see there are some blue stars, there are some red stars, lots of different color stars. Remember that if you see blue stars somewhere, that means there's active star formation occurring, because blue stars burn out very quickly, right? An O-class star, for example, could live for no more than 1 million years, say. And so if you see a blue star, you know that it must have formed pretty recently, because if it hadn't, it would be dead by now. On the other hand, a globular star cluster is an older star cluster which does not have very much active star formation, and so that's reflected here in the fact that the vast majority of these stars are orange or red. So these are older, cooler stars. So summarize, an open star cluster is full of young stars, and a globular star cluster is full of old stars. Now, because all of the stars in a cluster are born at the same time, it turns out that we can actually use the HR diagram to learn something about a star cluster's age. So we're going to be very schematic about it, at this point, just to avoid confusing details, but here, so if we look at a sketch of the HR diagram, which we kind of simplified to just have a linear sort of relationship between the, well, a line anyway, going sort of bottom right to upper left between the luminosity and the temperature. When the star cluster first forms, everything will be on the main sequence, right? Because nothing has had time to evolve off of it. But as the stars evolve, say after 100 million years, the most massive of those stars will have left the main sequence. And so after 100 million years, the HR diagram might look something like this. And this, at this point, we can define something known as the main sequence turnoff point. And it is what it looks like. It's the point at which the stars, as plotted on the HR diagram, turn off of their original main sequence. If you go 10 billion years from formation, you can do the same thing, but what will happen is that the main sequence turnoff point will move down to the bottom right. Whereas in the early going, only the very hottest, most luminous stars will have left the main sequence because they burn faster, they burn hotter, and they exhaust their hydrogen fuel more quickly. After 10 billion years, you've gotten to the point where even plain vanilla stars like the Sun, a G-class star, will have left the main sequence. And so the result is that there's a clear relationship between the location of the main sequence turnoff point on the HR diagram and the age of a star cluster. And so now that we know that, we can work the other way, plot the stars of a given star cluster on the HR diagram, look at where the turnoff point is, and thereby determine the age of the cluster. So let's look at an example. Here I've plotted the shape of the HR diagram for 4 different star clusters. And my question to you is, which cluster is the oldest? So as usual, I'll pause here for 30 seconds or so, and then we'll come back and see what the answer is. Okay, well, as always, you're welcome to mute me and or pause the video and think as long as you like. But I'm going to answer the question now. So as I mentioned, when we look at the HR diagram, at the beginning of a cluster's formation, there is no turnoff point, right? Because no stars have left the main sequence. So as the cluster ages, the turnoff point moves from the upper left towards the bottom right. And so on this particular plot, the Pleiades represent the youngest star cluster. Lots of young, hot stars are still present there. Next, oldest, we have NGC 1866. Next, we have Precipe. I can't promise I pronounced that properly. But then finally, the oldest cluster here, which has the turnoff point lowest and rightest in the HR diagram, is NGC 752. And there you have it. So here's an example of an HR diagram of a star cluster plotted with real data. And in case you're interested, here at the bottom, I've superimposed the spectral classification here so you can kind of see where the different stellar classes are here. But you can see the turnoff point right here quite conspicuously, right? So you've got red dwarfs down here at the cool end of the spectrum. These things can live for 100 billion years, up to 500 billion years. So they're going to be around for a long, long time. The main sequence extends up here. But then for this particular cluster, you can see the main sequence turnoff point is just a little bit above one solar luminosity, right? So, and then you have what we haven't talked about, but what they call the subgiant branch, which is just this little sort of kink section here, and then the red giant branch. Then you have an asymptotic giant branch and the horizontal branch. And obviously you have some white dwarfs that have already formed as well. So that tells you, that the stars of this cluster has been around for a while because it's been there long enough to create quite a few white dwarfs. And so if you had data from a number of other star clusters, you could make the comparison and you could figure out, well, given the location of this main sequence turnout point, how old is this cluster? So let's ask a related question now. Coming back to this comparison between the open star cluster, which is full of young stars, and a globular star cluster, which is full of old stars, which star cluster is likely to contain more heavy elements? So you're thinking iron and above, by which I mean heavy elements. So again, I'll pause here for 30 seconds, and then we'll talk about it. Okay, well, you may or may not find this answer counterintuitive, but the key to understanding the prevalence of or relative lack of heavy elements is to remember what is it that creates heavy elements. So any element of higher atomic number than iron is produced during an R process. Well, in order for the R process to occur, you need to have very massive stars. Now, those massive stars necessarily exist in young star clusters as opposed to old star clusters, because if the star cluster is old, there are no young stars anymore. There are no massive stars anymore. The massive stars have burnt out. And so, as you might expect now, the open star clusters could be expected to have more heavy elements. They have the young stars, the hot blue stars that you can see here in the picture that are capable of producing those heavy elements, both through the S process that leads up to iron. So even if you think about silicon, sulfur, neon, magnesium, and iron, those are heavier elements that are not produced at all in low mass stars. But then, in addition to that, in the R process that exists only in the case of massive stars, supernova explosions, those can only exist for these very massive stars. So that brings us to the end of our discussion of the evolution of high mass stars. So congratulations, you made it through 3 lectures on the evolution of low mass stars and 2 lectures on the evolution of high mass stars, and so now you're an expert in the evolution of all stellar classes. Going forward now, we'll finally have some more time to talk about some of the most sort of exotic aspects or objects in the universe. We'll talk a little bit about general relativity because that's going to be required to understand things about how neutron stars and black holes and such exist and their influence in the universe. So a lot of exciting stuff. I know if you've been with us the whole time, then you've suffered through plenty of me, and so for that I apologize, but I promise that we're to the really exciting part now. And so I hope that you will enjoy it, and I hope you'll stick with us the rest of the way. So thanks for your attention today, and I will look forward to seeing you back here for lecture 22.